All right, so let us start now with the Thevenin's theorem. Okay, so let me just open a notepad. Okay, so in Thevenin's theorem, okay, so we have this terminologies like RTH, VTH, and then of course the R. Of course, you guys already know this one. This is the R load, okay, or the load resistance, and then RTH is the Thevenin's resistance. Okay, let me just make this one bigger. And then Thevenin's voltage. Okay, so those are the things that you guys need to find when it comes to Thevenin's theorem. Okay, so this one is quite similar with the Norton's theorem. Okay, so the counterpart of RTH in Norton's, we call that one IN, okay, or I Norton exact, but just uh, make it short as IN. Okay, not in, but it's IN or I Norton. Okay, this one is the Norton's current. My bad. Not the counterpart of RTH, but it's the counterpart of the VTH. Okay, so for the Norton's resistance, okay, so this one is ITH. Okay, uh, RN, not ITH. Okay, so Norton's resistance and then Norton's current. Okay. So as early as of now, I would like you guys to know that the way that we solve for the RTH is the same on how we solve for the RN. Okay, so it's like hitting two birds with one stone. So with that, we could say that they are really super similar. They just differs when it comes to this one has a current, but this one has a voltage source. Okay, so of course this one also has an RL or the R. Okay, all right. So enough with the terminology. So let's start now with the Thevenin's theorem. So the Thevenin's theorem is another theorem wherein, oops, sumasabra. Is another theorem, of course, that make possibilities that wherein we can simplify any linear circuit, no matter how complex it is. Okay, as long as it's a linear circuit, but we can convert that one into a Thevenin's circuit, and then find the RTH and then the VTH and then the individual currents and then the individual voltage drops on that circuit. Okay, so again, as long as it's linear and then there's no exponents or roots on that circuit. Okay, so if we have resistors, inductors, and capacitors, that is possible. But if we have gas discharge or semiconductor components, that is not possible because that's already a non-linear circuit. Okay, so just do take note on the limitation again of the Thevenin's theorem. This one is only possible if we have a linear circuit. So without a further delay, let's use again the same example. So as you guys can see, we're still using the same example from Maxwell to superposition to nodal voltage and then to uh, Thevenin's theorem. So that's because we would like to, compare, okay, how they differ when it comes to solving the voltage drops on R1, voltage drop on R2, voltage drop on R3, the current on this right side, the current on this left side, etc., etc. Okay. So with that being said, let's use this as our example in this Thevenin theorem. So the first thing that you guys need to do, okay, is where or identify where is the load. So that depends on the question. So this could be a load, this could be also a load, okay, or this could be a load. So in this particular example, the chosen load is this R2 right here, okay. So just do take note that a load can be found anywhere on the circuit. Okay, it's just that the load right here right now is the one that is in the middle, which is the R2. Okay, so once you find the load or the R load, so just remove that one. Okay, that's the first step when it comes to Thevenin equivalent circuit. So after removing that one, okay, so where is that remove? Okay, so you will have this circuit, but before that, let's go right here. Okay, So our goal, okay, is to convert this original circuit into this Thevenin equivalent circuit. So going back with our terminologies, so the one that we are solving when it comes to Thevenin's theorem is the RTH, VTH, and then the RL. So RL is already given, so no need to solve for that one. But for the RTH and then VTH or ETH, so those are the things that we need to calculate. Okay, so once you have the values of RTH and then the ETH, then you can now have this one as your final circuit for the Thevenin equivalent circuit. And then from here, you can now calculate the current that is flowing on R2, current that is flowing on R Thevenin, the total current, the voltage drop on this one, the voltage drop on this R load, and so on and so forth. Okay, so yeah, that's basically it for the Thevenin's theorem. Okay, but of course, how do we solve for the R Thevenin and then E Thevenin? So we have this step-by-step solution right here, but just to make it short, okay, enough with the explanations. I'll leave the reading part to you guys. So first, the chosen load resistor is removed from the original circuit, replaced with a break or open circuit. Okay, or break it or just leave it open. So that is the first step. Okay, after removing that one, then you can now solve for the voltage drop on R1, voltage drop on R3, the total voltage drop, the current on R1, the current on R3, the total current, okay, and then of course they're given values of resistance, okay, which is 4 ohms, 1 ohm, and then the total resistance, which is 5 ohms. Okay. Now, how did we arrive with those values? So you can use any law that you can think. Okay, you can think of. So you can use Ohm's law in here. You can even use Kirchhoff's voltage law. Okay, you can even use superposition theorem if you want, since that's also possible. Since we have two voltage source in here, you can even use nodal voltage analysis if you want. Okay, so any theorem that you can apply to find the RTH and VTH, so you can use that one. Okay, now let's have now the solution for the RTH. Okay, let me just copy this one. Okay, so the original circuit, oops. So the original circuit was this one. Okay, and then of course the first step is to remove the R load. Then after that, we will arrive with this kind of circuit. Okay, so we now have an open RL right here. Okay, so now where can we solve? Okay, where can we solve for the RTH? Okay, where can we solve that one? Because there is no indicator that this is the part where we can solve for the VTH, this is the part where we can solve for the RTH, and so on and so forth. So wherever is your RL or your load resistors, load resistor, there's only one load resistor. Okay, so that is where you can find the value of RTH and VTH. Okay, so in other words, this is where you can find the RTH and the VTH. This open circuit right here. Okay, so I hope we're clear with that one, because some know the steps, like for example on how to solve the RTH and VTH, but they don't know where to solve the RTH and VTH. Okay, so wherever is your load resistor, that is where you can find the RTH and VTH. So in this case, we're going to solve for the RTH first. Okay, solving for RTH. Okay, so in here, in order for us to solve for the RTH, we have another step that we need to do. Okay, so after removing the load resistor or after opening that one, so we have to remove all the voltage or current sources. Okay, that is the second step for us to be able to find the RTH. Okay, so as simple as that. So just remove the voltage sources. So we only have voltage sources, so just remove that one. So we actually have the same rule with, I don't know if it's a superposition theorem. Yes, it's superposition theorem. If it's a voltage source, okay, let's just see Vs. Okay, okay, just short it. Okay, and then if it's a current source, so Cs for current source, just break it, okay, or leave it open. So in here, as you guys can see, we have voltage source for the B1 and then B2. So just simply short this one. Okay, I'll remove this one and remove that one. And then just connect this one. Okay, so there you go. So from here, as you guys can see, we can now easily combine those two resistance. So, RTH is actually like solving for the total resistance. Okay, so as you guys can see right here, like solving for the total resistance of this entire circuit, the R1 and R3. Okay, but before you can do that one, just take note that we didn't completely open this section right here. Okay, so if this one is completely open, well, of course, we now have a series connection, but it's not. Okay, this one is now actually our node A. Okay, and this one now is our node B. Okay, and then if you guys are going to transform this one, okay, from here we have the node A and node B, and then this is the part wherein we have this line right here. Oops. And then we have this resistor for R1, and then we have this resistor for R3. Okay, and as you guys can see, they are not in series at all. Okay, they are actually in parallel with each other due to this node A and node B. Okay, so for us to be able to find the RTH, okay, so we have to apply the rules of parallel connection. Okay, so RTH is equal to R1 times R3 divided by R1 plus R3. Okay, and then from here, R1 is equal to 4 ohms, and then R3 is 1 ohm divided by no need for parentheses, so 4 for R1 and then 1 for R3. So in here you'll arrive with 4 divided by 4 times 1 is 4, and then 4 plus 1 is 5. Okay, wherein 4 over 5 is, I think, 0.8. Please verify if this is 0.8 ohms. Please check this one using your calculator, and then let me know if 0.8 is correct or no.
Correct, sir.
Correct. Okay. So that is if we have the R load in here. Okay. But what if we have the, okay, tanggalin ko na muna to. But what if we have the R load in here? Let's say this is now the part wherein it is open. So we have here now the node A and then node B. So since we don't have nodes in here anymore, so just simply add them. Okay, so that's already your RTH. So 4 plus 1 is your RTH. But since we have a node in here, so forming a parallel connection, so that is why we have 0.8 as your RTH. Okay, so the same scenario, if we have the, let's say, the R load in here on the bottom part, so we have the node B right here and then the node A, or node A or node B. So this one will form is a series connection, okay, R1 plus R3. Okay, so that one really completely depends on the placement of your R load. Okay, so I hope we're clear with that one. Okay, so that depends now on your analysis on how you analyze the circuit. Okay, are they in series, are they in parallel, etc., etc. Okay, so this is already our answer for the RTH. Okay, as simple as that. So the only remaining one right now is the VTH. So let's solve for the VTH. So solving for VTH. Okay. Now, in solving for VTH, of course, we need to bring back the voltages that we just removed a while ago. Okay. So from here, let me copy this one again. Okay. And then, of course, we have to leave this one open. Okay. And this is now the part where we can find the VTH. Okay. Now, in solving for the VTH, that one is actually super simple. So as you guys can see, if you are going to analyze this one, okay, just the knowledge that you've learned on how to analyze a circuit. Okay, so as you guys may all know, we have a current that is flowing here. So we have this 28 voltage source. So from a negative to positive. So the same with the right side. So we have the negative and then the positive. So we have a flow of current from this point to this point. Okay. Then of course, this voltage source will pass through this R1. Of course, it will have a voltage drop. Okay, so the same with this B2 right here upon passing through this right here. So you're going to have a voltage drop on R3. So whatever is a potential voltage of this left side area and then the right side area will be combined as one as your VTH. Okay, now how do we do that one? Okay, so in here we can actually apply. Okay, we can apply Kirchhoff's voltage law for us to be able to find the single current that is flowing in here. So applying uh, applying applying KVL to find the total current. Okay, the single total current. Okay. So in here, of course, one voltage source will dominate the entire circuit. Okay, there's no way that both of them will function at the same time. There is always one voltage source that will dominate the entire circuit. So as you guys can see right here, if you guys are going to analyze this one, so we have a higher voltage source on the left side. So it's only a common sense, okay, that we're going to have this kind of flow of circuit. Okay, from left side to right side. Okay, so from here we can now have bakit yun ulit? We can now have a positive 28. Okay, so para hindi kayo malito, let me just put the signages. So negative here, positive here. Of course, it will give you a voltage drop in here. So positive and then negative. And in here, it's positive and then negative. And then we have here positive and then negative. Going back here is 0. So if you guys are confused in some parts, so just ask me, okay? So from here, we will get positive 28 minus I, or the current, or the total current, times R1, okay? Minus I times R3, and then minus 7 volts. Going back to the original voltage source, it's now equal to 0. Okay, so we now have your equation for the KVL. So time check, it's 1 minute left. So since we don't have enough time anymore, so we'll just continue the rest on the part 2. So for now, goodbye and then see you guys later. Okay. Okay. Alright, so let me just check if you guys are right in front of your computer. So go ahead and just give me thumbs up. So 5 out of 9. Okay. So any questions so far up to this point before we continue the solution for the VTH? Questions or clarification? So were you guys able to follow everything?
Yes, sir. So far.
Okay, very good. All right, so in here, just substitute the given values for the R1 and R3. So 28 minus I times R1 is 4 minus I again, and then R3 is 1 minus 7 is equal to 0. And then from here, you can add similar terms. So 28 minus 7 is 21 minus, so we have two the same current in here. So I4 minus I1, okay, or plus minus I1 is equal to I5, okay, since they have the same polarity, negative and negative. And then equal to 0. And then from here, you can now transpose the I, or the current on the other side, will give us I5, okay, I5, okay. And then from here, we can now solve the value of I, okay. I is equal to 21 divided by 5. We're in 21 divided by 5. So anyone, please solve this one. It's 4.2, am I correct?
Yes, sir.
4.2 ampere, okay. So in here, after getting the current, we can now get the voltage drop across R1, and then from there we can now solve the potential voltage of this B1 in here to this node right here. So the same with the B2, okay. What is his potential voltage on this node right here, okay. So let me just put here the uh, nodes, node A and B, okay. So for us to be able to find the PVB, oops, bakit yun ulit? Okay, potential voltage of B1, PB1, potential voltage na ba? PBB1 na lang. Okay. So after passing through these R1 right here, so we have to get the original voltage source value minus the voltage drop, okay, across R1. Okay. So in here, V1 is of course 28 minus VR1. Okay, so of course we have to solve for the VR1. So VR1 is equal to I1 times R1. Okay, just apply Ohm's law. So in here, we only have a single current. So the current on the R1 is the same with R3. Okay, so I1 is equal to I. So VR1 is equal to 4.2 times R1, which is 4 ohms. So VR1 is equal to 16.8. Okay. And then let me just copy this one and then paste it again right here. So VR1 now is 16.8. So 28 minus 16.8. Okay. So this is one way for you to be able to identify what is the VTH, or the voltage that is flowing in here. Okay. Using the left side uh, let's say circuit. Okay, so 28 minus 16.8 is 11.2. Yeah, so please check, is it correct? 11.2 volts. Correct, correct. 28 minus 16.8.
Yes, sir.
Okay, So from here, we can already see that this is our VTH. So the potential voltage on the left side that is passing through here is already our VTH. Okay, but of course, we have to verify this one. Okay, how? Then we have to apply the same on the right side circuit. So let's have another computation. So let's call this one PB B2, the potential voltage of this B2 right here. So the same, we have B2 minus VRT, okay, the voltage drop across R3. So P is equal to 7 minus VR3. So we have to solve for the VR3. VR3 is equal to I3 times R3. Okay. So VR3 is equal to, so our current again is 1 only. Okay. So we have 4.2 amps multiplied to 1, okay, which is our R3. So VR3 is equal to 4.2 volts. Okay. And then from here, we can now substitute this one. So VR3 is 4.2 volts. Okay, and then B2 is 7 volts. Okay. Oops, my bad. Parang may mali. Positive 7. I see. My bad. So it's not negative. Okay. Since if you guys are going to take a look on this one, we have the positive sign right here, which is correct, 7. But in here, going from here to there, so we're considering the outer sign. So it's positive VR3. So in this case, it's not a voltage drop, but it will be added with our voltage on the B2. So this one will become positive, positive, and then positive. Okay. So 7 plus 4.2 is equal to 11.2 volts, which is also equal with our VTH. So voila, from here, we now have, or we have just confirmed that the correct value of VTH is really 11.2 volts. Okay, so yeah, we have now solved the value of VTH. Okay. So you can find the VTH on the left side part, okay, or on the right side part. So either of those two. So are we clear so far to this point? Okay, so what about the others? Hmm. Okay, so there we go again. I'm not sure if you guys are in front of your computers. So anyway, so once you already have the value of RTH and then VTH, then you can now have this kind of circuit. Okay, so where is that one? Okay, so let me just copy this one so that we can have a faster discussion. So there you go. From here, we have the ETH or the Thevenin's voltage, which is 11.2. And then we have the RTH, which is 0.8 ohms. And then whatever is the original value of your R2, just place it right here as your R load. Okay, so just do take note that there is no other implementation of Thevenin equivalent circuit, okay, other than this one. So this is the default uh, circuit that you have to use. Okay, so the positioning of your E Thevenin is on this side, okay, and then the positioning of your R Thevenin is on this side or the upper left, and then your I load is always on the right side, okay, which is this one. And then from here we can now solve for the uh, ano nga ba? Okay, what is the question in here? Let me just check on what we are trying to find as our answer. Determine the voltage. Okay, so the only question is determine the voltage across the load resistor. So for us to be able to determine the voltage across right here, okay, so we have to find so we can add this one first as our R total. And we can find now the total current and then solve for the voltage drop. Okay, so let's do that one. So let's find the R total first. So it's super easy since they are in series connection. So R total is equal to R Thevenin plus the R load. R Thevenin is 0.8 and then R load is 2 ohms. So 0.8 plus 2 is 2.8. Okay. And then from there, we can now find the total current. Okay, I total is of course V total. Let's just say VT divided by R total, okay, or RT, wherein V total is 11.2 volts divided by R total, which is 2.8 ohms, and then 11.2 divided by 2.8. So anyone, please check what is the value of this one. Okay, ko yung calculator ko. Dito. 11.2 divided by 2.8 is equal to 4 amps. Okay. So once we have the value of our total current, then we can now apply that one to find the voltage drop across our load resistance. So VRL is equal to I total times R2. Okay, wherein I total is 4 ohms times the R load, which is 2 ohms. So 4 times 2 is 8 volts. And then knowing that we have an 8 volts right here, then we could just simply say that R Thevenin has a voltage drop of 3.2. Yeah. But if you want to verify that one using Ohm's law, so we can also use this one. So VRTH, so again IT times RTH. So 4 times 0.8 will give us a value of 4 times 0.8 is 3.2. Okay. Having a total of 11.2 volts as your original voltage source. Okay. So this is already our answer for that one. So let me just put this one for you guys to be able to check. So this is already our final answer for this example since that's the only question. Okay. So for the current, of course, we only have a single current, which is 4 amps right here, 4 amps right here, and then 4 amps right here, since this one is in a series connection. Okay, so if we are going to compare that one using this table right here, those individual currents and then individual voltage drops, we'll arrive with this. With this table. So the voltage across R Thevenin is 3.2, okay, which is this one. And then the, ito ba yun? May bad. Okay, so our final answer is 8 volts. Okay, since the one that we are looking for is the voltage drop across load resistor, not across the R Thevenin. Okay, so this is the final answer, which is 8 volts, which is this one, ER load. And then the E total is, of course, 11.2. And then the current is 1 only, which is 444. And then the resistance, which is already given, 0.8 and then 2 and then the total resistance, which is 2.8. So are you guys able to follow?
Yes, sir. Sundan naman po.
Okay, very good. So mostly the question when it comes to Thevenin's theorem is what is the voltage that is flowing on our R load, or what is the current that is flowing on our R load. Okay. So ganun lang naman pagdating sa mga Thevenin's theorem. For some cases siguro ipapasolve sa inyo kung ano yung voltage across R Thevenin, but mostly sa R load. Okay. So ito na yung lahat. These are all the possibilities that we can solve with this kind of circuit. Okay. So yeah, that's already it for the first example. Okay. And then if you guys need more example, okay, like more basic examples, you can visit this English video example. And if you want a Tagalog version of video, okay, or a tutorial, please visit this one. Okay. So let's check this Tagalog video example since I need to mention something in here. So initially, it will give you this complicated circuit. Okay, but of course, with the analysis of using Ohm's law, you'll be able to reduce this one into a super simplified circuit, like this kind of circuit. Okay, so this is a 16-minute video, which is super helpful on how to analyze this one and then simplify that one into a super simplified circuit. Okay, so the main goal in here is, I think, to find the voltage across the RL. So let's verify that one. Bakit ayaw? Where is the question? So he's also going to teach you the step-by-step, okay, on how to solve the RTH, how to solve the VTH. Okay, it's now a little bit lagging. Anong nangyari? Okay, so here's the simplified version of that one, I guess, after forming, after having this complicated circuit into this one, and then this is now the, where is that one? This is now the more simplified version of that one. However, of course, this one is still not complete since we still have to compute for the RTH and then the VTH. So in here, the question here is define the Thevenin equivalent circuit of the circuit shown below to the left of the terminals AB. Okay, from here A to B. Okay, then find the current through RL. Okay, which initially it's 6 ohms. So you're going to have three computations. But thanks to Thevenin's theorem, so all you need to do is change the value of RL once you've arrived with this kind of equation. So that is the advantage of having a Thevenin's theorem. So if there is one change, one changes in this particular circuit, we can actually apply Thevenin's theorem for you to be able to have uh, a faster way of solving that one. For example, the current on this RL, okay, if it has a resistance of 6, the current of on that RL, if we have a resistance of 16 or 36, okay. So just imagine this one as, it could be any appliances. So it could be a refrigerator, it could be a television. So it's like you're trying to solve what is the current that is flowing, okay, on this point right here. If we have a television, if we have a refrigerator, if we have a call this one, let's say an soldering iron, okay. Ano ba yung tawag doon? Plancha. Uh, Iron tawag doon, di ba, sa English? Pero parang may mali. Tama ba? Iron lang? English of plancha. Because soldering iron is the one that, yung panghinang. Plancha is scaffolding. Tama ba to? Yeah, iron. Well, anyway, I think it's the correct terminology for that one is scaffolding. Well, I don't know with that one. So yeah, you could imagine this one as any appliances, and then if you want to solve the current, okay, this load resistance right here, or the appliances right here, so you can apply a Thevenin's theorem. Well, as long as you know the circuitry or the resistance that is flowing on your entire house. Okay. Well, anyway, so yeah, just watch this one, and then I'll teach you on how to solve this kind of circuit. Okay, because the one that I have in here is a super simple circuit. Okay, so are we clear with that one, guys?
Yes, sir.
Hello, hello. So any questions so far with our solution right here? Okay, so I guess none. So let us now move on to the next example. Okay, so here's the, I think the summary. Yeah, just the summary. So in here, I will leave the reading part to you guys. Okay, because my only concern is on how to show the solution of this table right here. So in here, you can actually find the Thevenin's source first, okay, the VTH, or you can go with the RTH. So either of those two, I will be fine. Okay, so you can interchange any of those. And after that, you can now convert that one into a complete Thevenin equivalent circuit, and then you can now find the voltage drop across that R load, or the current that is flowing on that R load. Okay. So the reference of the slide 1 to slide 13 came from all about circuits. So the next example that I will be discussing to you guys is still under Thevenin's theorem. However, this one came from a different source, okay, or a different reference. This one came from uh, electronic tutorials, I guess. So we'll check that one later on. So in here, uh, the same concept, the same everything, just a different terminologies, and then different way of explaining things. Okay, so it says here that RL is a linear network containing several EMFs and resistances. Okay, so the one that we have a while ago are the linear components. Okay, so as long as they are in linear, then we can simplify that one, and then to solve for the RTH and then the VTH. Okay, so just do take note that in here, the VTH is equal to Vs. Okay, that's the term that they did use in here. So RTH is Rs, and then VTH is equal to Vs. So those two are just the same. Okay, so Rs for RTH, and then RL is still RL, okay, which is our R load. So again, we have a similar example, just different values. So we have 10 volts, 10 ohms, 20 ohms, 20 volts, and then 40 ohms. So in here, what is the one that we are looking for? Is found by, well, anyway, so we'll see what we are uh finding, okay, on this example, because I already forgot. Well, anyway, so the same concept on how to solve for the RTH. Okay, remove the resistance, okay, and then remove the voltage sources. So if it's a voltage source, just short it. If it's a current source, just leave it open. Okay, and then from here you can now find the RS, okay, or the RTH. So again, they are of course in parallel with each other due to this node A and B. So 10 times 20, okay, or 20 times 10 divided by 20 plus 10 will give you a value of 6.67 ohms. Okay, so are we clear so far on how did we get the RS or RTH on this example?
Yes,
Hello,
sir.
hello. Okay, so just take note on the solution for the RS, which is the RT. Okay, this is already our RS. So after that one, we can now solve for the voltage source. So in here, we can apply KVL again to find the current that is flowing on the entire circuit. So in here, okay, just wait a second. V divided by R. Okay. So what he did in here is not with the use of KVL, but simply with the use of Ohm's law. Okay. So in here, so I is equal to V divided by R, wherein he just did get the polarity. This one is a lot easier. Okay, since as you guys can see, we've just assumed that this is the correct polarity since we have a higher voltage source on the right side. So it's flowing from right to left. Okay, so positive 20 minus 10. So that's like our final voltage source already. Okay, so 20 minus 10. And then in here, he assumed that, of course, they are in series already since this is just in open path. So 20 plus 10 is equal to 30. So it's like 10 divided by 30 is equal to 0.33 amps. Okay, so that's for the current, okay, without applying KVL. So from here, you can already solve the voltage drop across this one and then the voltage drop across this one and then verify if we have the same result. If we have the same result, then that's the correct answer for your VTH. So in here, the potential voltage on the VAB, so I think this is the right side, 20, yeah, 20 volts. So this is the right side part minus the voltage drop, okay, which is 20 times 0.33 amps, you will get a voltage source of 13.33 or a Thevenin's voltage of 13.33 volts. So for you to be able to check if this one is correct, again, you can do the same on the left side. So it's 10 plus, so it's not a voltage drop, but then again, it's a addition due to the polarity, okay? So from left to right, okay? So 10 plus this value right here will give you 13.33 volts. Okay. So are we clear so far on how did we get the Vs and then the Rs? Hello, hello, hello. Are you guys still around?
Yes, sir.
Okay. So just let me know if you guys have a question, okay? Since I'm making this one real quick since this one has a complete solution anyway. Okay. And then after that, of course, you can now put here your voltage source and then your Thevenin's resistance. And then from here, you can now apply Ohm's law again for you to be able to find the total current. And then you can now find the voltage drop across this RL or the voltage drop across this RTH or the RS. Okay, so it's already in here. Just double check this one. Okay. So as a conclusion, Thevenin's theorem can be used as another type of circuit analysis method and is particularly useful in the analysis of complicated circuits consisting of one or more voltage or current source and resistors that are arranged in the usual parallel and series connections. While Thevenin's circuit theorem can be described mathematically in terms of current and voltage, it is not powerful as mesh current analysis or nodal voltage analysis in larger networks because the use of mesh or nodal analysis is usually necessary in any Thevenin exercise. Okay, so parang ganun na nga, kahit na meron tayong sariling theorem na let's say Thevenin's theorem, we're still heavily relying on the other theorems like KVL. There's always a KVL, there's always a KCL, there's always an Ohm's law, okay, for us to be able to check if our values are really correct or no. Okay. So, however, okay, Thevenin's equivalent circuits of transistors, voltage sources such as batteries, etc., are very useful in circuit design, just like what we have in here. Okay, so if you have, oops, hindi ito yun. So if you have this kind of circuit, you can easily replace this one, without redoing all of your computations. So that's again the main advantage of using a Thevenin's theorem. Okay, so you can replace this one, okay, without recomputing or recalculating all of your computations. Okay, so ito lang, and then you can recalculate again for the total current and so on and so forth. So additional summary. So we have seen that the Thevenin's theorem is another type of circuit analysis tool that can be used to reduce any complicated electrical network into a simple circuit consisting of a single voltage source, which is the Vs in series, with a single resistor, which is the Rs. Okay, and then when looking back from terminals A and B, this single circuit behaves in exactly the same way electrically as the complex circuit it replaces. Okay, that is the uh, IV relationship. Terminals AB are identical. Okay, so here are the basic procedures, but then again, you can interchange the number 20. So you can find the VS or VTH first before the RS or RTH. But mostly, we can go with RTH because this one is a lot easier than solving for the VTH or VS. And after that, you can now find the current, okay, that is flowing on the RL, or the voltage drop that is flowing on the RL. So yeah, the reference where this one came from is from electronics tutorials. Okay, and yeah, that's it for this module, for module 7. So are we clear so far? Hello, are you guys still around, or are you guys already eating?
Yes, sir. Still around.
Okay, so hang in there. We still have one more module to discuss. Okay, so again, if you guys need more example, then you can always visit this watch videos. So I did put here 5 links, I guess. Yeah, 5 links. So 3 for the Thevenins and then 2 for the Norton's theorem. Okay. So if you guys don't have a question anymore for the Thevenin's theorem, then we can now move on to the Norton's theorem, which is the module 8. Now, this one now is super easy, since learning about Thevenin's theorem is like learning the 50% of the Norton's theorem already. Okay, so what is that 50%? So just like what I mentioned a while ago, whatever is our process on how to solve the RTH or the RS or the Thevenin's resistance is the same on how to solve for the RN, okay, or the Norton's resistance. Mali ito. Norton's resistance. Okay, so there you go. Okay, they just differ when it comes to solving the sources. So in here we have a current source, but in here we have a voltage source. Okay, so without a further delay, let's start. Okay, so we still have 2 minutes, so let's maximize our time. So again, the same concept. So we can convert any linear circuit into super simplified circuit, like in Norton's equivalent circuit, as long as it's a linear circuit. Okay, it doesn't have exponents or roots. Okay, so again, for you to verify, able to verify if it's a linear circuit, so if it only contains a voltage source, current source, resistance, capacitor, okay. For in some cases, yeah, inductor is also linear, but there are some debate, okay, or issues wherein saying that inductor is not a linear component. Well, anyway, just to be sure, okay, we only have 3 components for linear. Okay, resistors, kasama pala. Okay, well, anyway, so parang apat, okay, yung parang i-consider nyo. So resistors, inductors, capacitors, and then of course the voltage sources. But if you have components like gas discharge or any semiconductor components, that's already a nonlinear circuits. Okay, so with that, you cannot apply Thevenin's or Norton's theorem on that specific problem, okay, or specific circuit. Well, anyway, so since we don't have enough time again anymore, so we'll just continue this one later on, okay, on the part 3. So again, goodbye for now, and then see you guys later. Okay, so pabawas ng pabawas. Kanina, 11 yata kayo or 12. Tapos naging 9 or 8 na lang yata ng part 2. And then ngayon, 7 na lang. Okay. So, it's only normal. Alright. So, are you guys still okay? Kaya pa ba?
Kaya pa po.
Kaya pa. Okay.
Kaya pa.
So, don't you guys worry. Okay. So, I just really think, okay, in my own way of thinking. Okay. So, when it comes to finals, Thevenin's theorem and the Norton's theorem is the uh, super, uh, well, depende kasi. Like, for example, if you guys are going to take a look on this one, yes, applying the, the concept of Thevenin's theorem and the Norton's theorem is super easy. However, on how you simplify things or how you analyze things. Okay, like for example, parallel ba ito? Okay, magko-combine ba sila? Okay, ano ba yung magiging parang circuit ko na kapag katapos kong makombine, etc. etc. Okay, so baka dun kasi nagkakamali pala. So that is why uh, fundamentals is very important. Okay, so solve a lot of parallel circuit, learn how to simplify them properly. Okay, because in my case, hindi ko siya matuturo talaga. Ayun na mismo yung parang makaka-realize. Okay, so sinasabi ko lang na siguro the simplest way is if this one is a node, okay, and then it has another components in here, then this one is already in parallel connection, okay. But if there is no other, if this is not a node, and then there is no other components on that node, then that is a series connection, okay. So I think yun na yung pinaka-clue nyo kung sa tingin nyo series ba sila or parallel ba. Okay, baka doon pa lang kasi medyo madadali na kayo. Oops. Okay, so dapat practice lang, okay, when it comes to simplifying things on Thevenin's theorem or Norton's theorem. Okay, so yes, it's easy, but it needs a lot of practice for you to be able to master and how to simplify this kind of circuit. Okay, anyway, going back to our topic with Norton's theorem. Okay, so again, this one has the same uh, concept wherein you can simplify any linear circuit into a super simplified version, okay, as long as it doesn't have exponents or roots, okay. So let's use the same example, okay. So we have 28 for the R load and then 7 and then 1 right here. But our goal now is of course converting this one into a Norton equivalent circuit. So before we have a series connection. Okay, we have a series connection, E Thevenin, R Thevenin, and then R load. But on the Norton's theorem, okay, we now have a parallel connection. Okay, we have the I Norton right here, which is your current source, and then the R Norton, which is your computed resistance. Okay, and then the R load is still the same. Okay. Okay, so no important thing to mention. So yeah, just remember that this is the Norton's equivalent circuit. So with that, let's be so I'll leave the reading part to you guys. So I already discussed what is the I Norton and then R Norton, which is this one RN and then IN, and the same concept of course. So you have to remove the load resistor, and then after that you can remove your voltage sources. So if it's a voltage source, just simply short it, and then you can now find the total resistance or the uh, uh, ano bang tawag dito? RN, okay, Norton's resistance. Okay, so the same concept, okay, apply this one. Okay, you will have this R1 and R3, and then they are now in parallel connection since we have node A and node B right here. And then the one that you will get is of course a 0.8 ohms. Okay, so after solving the uh, RN, okay, lagi ko na lang nakakalimutan. So RN is the Norton's resistance. Then you can now find the Norton current. Okay, so I would say that Norton current or Norton current source is a lot easier to solve than the VTH, or the Thevenin's voltage source. Why? Because just simply Ohm's law, apply Ohm's law on this one, and then Ohm's law on this one, and then you can now find the current that is flowing in here, and then the current that is flowing in here, and then you can just simply add them, and then you now have the Norton's current. Okay, so in what way? So if you guys are going to take a look on this one, okay, so we have a current that is flowing from here to there, from here to there, and then just by applying Ohm's law, okay, I is equal to B divided by R. So let's apply this one on the left side first. Okay, so I is of course unknown, but V is 28 volts, and then R is 4 ohms. So that 28 divided by 4 is 7 ampere, or 7 amps. So with that, we already know that we have a current that is, a 7 amp that is flowing on the left side. So on the right side, same, I is equal to V divided by R. I is equal to 7 divided by 1. So 7 divided by 1 is 7 amps also. Okay. And then with that, let's just see that we're going to apply KCL, okay, on this node A. And let's say this is our node B. Okay, so KCL at node A, okay, is equal to, let's say, we need, say, I1, and then this is our I3, and then this is our I2. Okay, so again, going in to a node is positive, and then going out to a certain node is negative. Okay, just remember that one when it comes to KCL. And then from here, as you guys can see, we have I1 going in, and then I3, which is also going in. So I plus I2 minus I2 is equal to 0. And then from here, the one that we are looking for is the I2, since that is the unknown. Okay, so I2 is equal to I1 plus I3. Okay, I2 is unknown. I1 is 7 amps, right here, the left side area. And then I3 is 7 amps also, which is the one that is on the right side. So I2 is 14. Okay, so there you go. Oops, sorry. So that is why we have this 14 amps right here, which is this one. Okay, so our RTH, I mean RN, bakit laging RTH? Rn is 0.8 ohms, and then In, Norton's current, is equal to 14 amps. So once you have those two variables, then you can now perform this kind of equivalence circuit. So just replace uh, the given values. So something complete. Okay, let me use this one as our complete circuit. Okay, so 0.8 for the R Norton, and then 14 amps for the I Norton. So were you guys able to follow?
Yes, sir.
Okay, so super easy with the use of Ohm's law. Okay, well, that depends on the circuit. Okay, so in here we can just simply apply Ohm's law, since we can easily identify the current on the left side, the same with the right side, and then just simply combine them, and you will have 14 amps. Okay, after that, you will now have this given values right here. So of course you can now find the voltage drop across R load, voltage drop across R Norton. Okay, to do that one, we have to solve, what can we solve right here? So of course we can solve the R total. R total is equal to R Norton, Rn in parallel with R load. So let me just copy and paste this one. So Rn, let's have a different equation since hindi natin ma-replace yan, of course. So Rn times RL divided by Rn plus RL. Okay, let me copy this one again. So just apply the rule of parallel connection for solving the resistance. Rn is 0.8, and then RL is 2, 0.8, 0.8, and then RL is 2. And then from here, we can now solve that this one is 1.6. Tama ba? 0.8, yeah, 1.6. And then 2.8. And then R total is equal to 1.6 divided by 2.8 is equal to 1.6 divided by 2.8 is 0.57. Okay, please check. Maybe I have a different answer. 0.57 ohms. Okay, so after having the R total, we can now find the V total. V total is equal to I total. IT na lang para mas malit. I total times the R total. I total is equal to 14 amps, which is our I Norton, times R total, which is 0.57 ohms. V total $7.98. So please verify also my answer. Okay, baka may mali. So we can recheck that one. So 7.98 volts. So okay, naalala ko na. Okay. So this one was actually rounded. Okay. Because if you guys are going to take a look on this one, ang total voltage natin is 8 volts. So for consistency, let's just round this 7.98 into 8 volts. Okay? Para lang magkaparehas yung nasa table natin. Okay? Then since they are in parallel, so the voltage across R Norton is of course 8 volts also. So ilagay ko na lang dito para mas madaling basahin. And the same, okay, our voltage across RL is also 8 volts. Okay, and the next one is maybe you would like to find the current across R Norton and then the current across R load. So that's also possible, of course. So IRN, okay, IR Norton is equal to the voltage, okay, across RN, IB divided by R, divided by the R Norton, which is RN. So IRN, so VRN or VR Norton is 8 volts divided by Rn, which is 0.8. So this will give us a value of 10 amps. Okay, and then solving for the IRL, okay, the current across this load resistance is so 8 pa rin kasi isa lang naman yung voltage voltage across natin if we have a parallel connection. So VRL is 8 volts and then RL. Okay, so for consistency, let me copy this one. VRL divided by RL. And 8 volts and then RL is 2 ohms. So 8 divided by 2 is 4 amps. Okay. So to check, kung tama ba yung current natin. So, of course, some current will flow in here, and then some current will flow on the R load. So, I total, which is equal to our I Norton. So, that's IRN. Oops. My bad. IRL to. And then IRL din to. May nabura yata ako ah. Ano ba? Parang may kulang. Okay, this is for the IRN. And then IRL. May nabura nga ako. Okay. Wait a second. IRN. And then VRN. And then RN. Okay. So there you go. So I total is equal to IRN plus IR. So that IRN is 10 amps and then IRL is 4 amps. Wherein it is correct. Yung nga lang para consistent tayo. 14 amps. So there you go. We now have the voltage drops or voltage across, which is 8 volts. And then the current across R Norton, okay, is 10 amps. And then the current across R load is 4 amps. Okay, so I hope you guys were able to follow. So let's check if we have the same result. Is it right here? So for the voltages, of course, we have 888 since they are in parallel. And then for the current, so we have 10 amps for the IRN. And then IRL is 4 amps, which is correct. And then the total current is 14 amps. And then for the resistances, so we have 0.8 right here for the R Norton, and then 2 ohms for the R load. And then we have here 571.43 milliamps. So this one is the same with 0.57 ohms. So for you to be able, baka hanggang ngayon, may nalilito pa rin sa milliamps saka amps ha. Milliamps saka milliohms, okay? Not amps, because this one is a resistance. So in here, if you want to have the, oops, mali. If you want to have the milliohms, okay, milliohms value, milliohms value, just multiply this ohms value to 1000. Okay, so in here we have 0.57. Just multiply that one to 1000, and then you will get 570. Okay, 570 na lang kasi wala na tayo ng mga ibang values like 1, 4, and 3 since I did only get the 2 decimals of this one. Pero kung tutuusin, ito yung exact value niya, 571.43 milliamps. Milliohms rather, not milliamps. Medyo unusual kasi yung milliohms, okay, na unit pagdating sa saan ko ba ilalagay ito para kita nyo. Anyway, so ganyan na lang. Ibaba ko na lang. There you go. So this one has a value of 570 milliohms. Okay. Which is the same with this one. Okay. So were you guys able to follow?
Yes, sir.
Okay, so I hope we're clear with Thevenin's theorem and then the Norton's theorem. Okay, anyway, so more explanation. So again, I will leave the reading part to you guys. And then here's a review. Okay, so kind of the same, removing the load resistors and then removing all the power sources. So we'll just short it. If it's a voltage source, just leave it open. If it's a current source, and then what else? And then from there you can now find the Norton's current and then the Norton's resistance to transform that one into a Norton equivalent circuit. Okay, so we have here another example. So let's have this one real quick. So we have 10 volts, 20 volts, 10, 20, and then 40 ohms. So the same concept, just remove this one. Let's say this is our R load. So remove the sender 40 ohm load resistor. So this is our R load. It's just that it wasn't able to put here this one as our RL, but this is our RL, the 40 ohm load resistor. Okay, so just short it. Okay, and then what else? Teka lang. Short out the terminals. Wait a second. What did we do in here? Ano bang hinahanap muna dito? So remove the power sources. The arrow notation when current source direction potential to calculate the Norton resistance. We do the exact the same thing as with Python. Yeah. Okay, so same naman. So yeah, I think it just wasn't shown in here, but you have to remove this one for you to be able to solve for the uh, Norton's resistance. Okay, so I did verify that one in here. So to calculate the Norton resistance or the R Norton, we do the exact the same thing as we did for calculating Thevenin resistance. So yeah, we have to leave this open and then combine those two, and then you will get 0.8 ohms using a parallel connection in here, R1 parallel to R3. So the same concept with what we have in here. After leaving this one open, okay, and then after removing the sources, okay, just short this one, okay. Hindi lang pinakita kasi solution na kaagad yun dito. But yeah, just short this voltage source right here. And then you can now combine this 10 ohms and then 20 ohms, okay, via parallel. So where is the computation for the R Norton? Kasi current to eh. Inuna niya yung current. Okay. Kaya pala medyo confusing. Okay? So, nag-start kasi siya sa pag-solve ng current. Okay? The Norton's current. So, of course, the thing that you need to do is, of course, short this one. Okay? Just like what we did in here. Okay? So, iso-short lang din natin to for us to be able to find the current on the left side and then the current on the right side. So, let's solve first the IN, okay, or the Norton's current para masundan natin to. So, for the I1, of course, ohms law lang, okay. So, I is equal to V divided by R. So, left side, 10 divided by 10 is 1 amp. So, the same with the right side, 20 divided by 20 is 1 amp. So, as you guys can see, we have the same flow of current that will merge on this node AB, okay, or this spot right here. So, of course, I1 plus I2 is now equal to our IN, okay, or I short circuit. Actually, IS naman yung tawag nila dito. Okay, IN is also equal with IS. Okay, that's the other different terminologies for that one. So in here, we also call it one, call this one as RS. Okay, so the same siya dito. Okay, then after that, we can now find the Norton's resistance. So remove the resistance right here, and then short the voltage sources, and then combine those two via parallel. So R1 times R2 divided by R1 plus R2, 20 times 10, and then 20 plus 10. So it will give you a value of 6.67 ohms. So with that, you now have the values for your IS or I Norton, and then RS or the R Norton. And then you can just simply put here the RL later on, which is this one. And then from here, you can now solve for the total resistance, and then you can now solve for the voltage across this RL or the VAB. Okay. So since it's already in here, and I think meron na lang tayong 12 minutes. Okay, so enough pa naman yung oras natin. But I will leave the computation part to you guys, since it's just a matter of, verifying whether this one is correct or no. Okay, just simply follow the given uh, equations right here, or the solution. So with that, you can now find the total current across your entire circuit. So just do take note that this IS right here is not our total current. Okay. Uh, Pag isosolve natin yung, teka lang, may bad. I think yun na yun. Okay. So, nire-retrieve ko yung sinabi ko. This is already our total current. Okay. So, yung meron tayo dito, okay, is the current across RL. So, may bad on that one. Okay. Which is 0.286 amps. And then, of course, some current will flow in here. Okay. The remaining current. And then more examples. Okay, so again, we have here the English video example, and then one Tagalog video example, which is the same with this one. So siya rin yung, sa kanya rin nang galing, dito kay Engineered Math. Okay, sa kanya din galing example for this Tagalog video example. Okay, and then here are the summary. Okay, so again, the first thing that you guys need to do is find where is RL, and then remove that one, and then you can now start solving for the RS and then the IS. Okay, so either of those two, you can interchange step 2 and step number 3. And then from there, you can now find, or you can now transform this one into a Norton's equivalent circuit, and then start finding the current across RL and then the voltage across RL. Okay. And then here is the reference for this topic right here. This one came from circuitglobe.com. My bad. Okay. Bakit ang gulo ko dito? So, ginawa ko pa kasi to last year, I guess. So, this one is just another info. Okay. But the source of this module, this one came from All About Circuits. Okay. And then some, okay, came from electronics tutorials. Okay, and then some of my ideas came from this YouTube video. Okay, and that's already it for the Thevenin's theorem and then the Norton's theorem. Okay, so time check, we still have 9 minutes and 17 seconds. So we still have plenty of time. So if you guys have a question, so feel free to ask me now. Or ako na lang magtanong. So were you guys able to follow so far the concept of the Thevenin's and Norton's theorem?
Yes, sir. Yes po.
Okay. So now that you guys have learned the basics, so please enhance more your your analyzing analysis, okay, analysis skill, okay, on how to analyze complicated circuits. So dito nyo malalaman kung talagang tama ba yung sagot nyo o hindi. Okay. So dito sa mga links na ito, okay, just try to visit these links right here. So we'll ask you some basic questions, okay, and then it will also show you the solution, of course, at the same time. So practice lang, okay. So just do take note that having two examples in one theorem is not enough, especially that that is your first time hearing about the theorem. Of course, I will teach to you, or most of the websites here in the internet will only teach you the super basic. So please explore more in answering complicated circuits. So you can find a lot of articles discussing about complicated circuits. Okay? So pwede nyo din siyang i-verify using other theorem. So that's the perk of having a lot of theorems, since you can verify whether your answer is really correct or no. Okay? And don't forget, hindi ko pa yata na-publish. Okay, let me just preload this one. Don't forget that you're going to have a quiz on Thevenin's quiz for this module. Okay, module 7 and 8, and then the same with Norton. The due date is June 29. Again, you guys have exactly 10 days for this one. The same with the case study number 4. Okay, so yeah, I think that's it. Those are the only things that I need to mention. So anyone who has a question or clarification so far? Or if none, then that's already it. So again, just give me a thumbs up, and then you guys be no go if you don't have a question anymore. Okay. All right. Okay. Okay. So thank you guys for coming. Okay, I really appreciate it. So goodbye and see you guys next meeting.
Bye, sir.
Goodbye. Goodbye. Question? Oops.